All right, let us continue our discussion on frequency response. We just got started with the definition of frequency response. We made the statement that if the region of convergence contains the unit circle, you can evaluate the Z transform along the unit circle. And we also made the observation that if the region of convergence contains the unit circle, then the impulse response is absolutely summable. And we are interested in the class of causal and stable systems. And further, we will focus our discussion on the class of systems whose input-output relationship is given by linear constant coefficient difference equation. We are focusing on this class because that is the only class that can be realized in practice. So, y of n is given by k going from 1 to cap n a k y of n minus k plus k going from 0 to cap m b k x of n minus k. So, this is the basic input output relationship that belongs to the class of LCC-DE. And now what we will do is we will look at the system's transfer function. We have already looked at the system transfer function for this class. We will just go through the steps quickly and recall the result. So, this is y of z minus k going from 1 to cap n a k z power minus k y of z plus k going from 0 to cap m b k z power minus k x of z, and hence y of z by x of z, this we denote as h of z, which is the system transfer function, and this turns out to be this is the denominator polynomial, and the numerator of course is k going from 0 to cap m b k z power minus k, and then we have seen that this is written in the form b of z over a of z. So, this is the transfer function corresponding to this class, and as we have made this point before, this is the class of rational transfer function, and the frequency response is h of z evaluated at z equal to e to the j omega. And when you are going to look at the frequency response of the above system, it is advantageous to write this in terms of the products of its poles and zeros. That is, we will factor the numerator polynomial and the denominator polynomial. Therefore, the denominator becomes k going from 1 to cap n 1 minus pk z inverse. All I have done is I have now expressed a of z in terms of its roots, and the numerator is k going from 1 to cap m 1 minus zk z inverse, where zk are the zeros and pk are the poles. This is not quite complete. To complete it, something more is needed, which is all I have done is I have written the numerator polynomial b of z in its product of its roots. Sorry, this should be the pi product. Okay. Now, what is missing here? this is not quite what the previous expression is. To make it exactly equal, what is needed is B naught. Very good. B naught is needed because without B naught, this, if you look at this, the z power 0 term, the coefficient will be 1, whereas the constant term for this polynomial is B naught. So, to make this equal, you need to have B naught here. And now we are going to evaluate this along the unit circle. Before we do that, let us do some further simplifications here. So, this is B naught. So, this is the pi product going from 1 to m. So, this is z minus zk by z. Similarly, in the denominator you have z minus pk by z. Of course, we are going to evaluate this along the unit circle. Now, if you look at this pi product, each term in the pi product has a denominator z. So, when you multiply this out, when you are done with, you will have z to the m in the denominator. Similarly, here you have z to the n in the denominator of the denominator. Therefore, if you simplify this, this will give rise to z to the n minus m. K going from 1 to cap m, this is z minus zk, and k going from 1 to cap n, z minus pk, all of this being evaluated along the unit circle. So, this is B naught. Now, we will substitute z by e to the j omega. So, this becomes e to the j omega n minus m, and this of course is k going from 1 to cap m e to the j omega minus zk, k going from 1 to cap n e to the j omega minus pk. So, this is the frequency transfer function, and the frequency transfer function, it is useful to think of it being expressed in this form. So, this is magnitude times e to the j phase angle, and no different from what you had seen in the continuous time case. So, this is the magnitude response, and this of course is the phase response, and we will study each of these parts separately. We will first focus on magnitude response and then on phase response. And hence, if you look at the magnitude response, this now becomes magnitude of B naught, magnitude of e to the j omega n minus m times k going from 1 to cap m, magnitude of the product is product of the magnitude. So, this becomes this, and in the denominator you have a similar term, and this of course is 1. And if you look at this term whose magnitude is 1, that factor is coming from z to the n minus m, and depending upon the values of n and m, z to the n minus m will be either a trivial pole or a trivial 0. If n were greater than m, this will be a trivial 0, otherwise it will be a trivial pole of order magnitude of n minus m. And hence, you see that this factor which is contributed either by trivial poles or trivial zeros as the case may be, they do not contribute to the magnitude response. And this is precisely the reason why poles or zeros at the origin are called trivial poles or trivial zeros, because they do not contribute to the magnitude frequency response. However, later we will see that they will indeed contribute to the phase response. You cannot have a term like z to the n minus m and not contribute to both magnitude and phase. So, it does not contribute to the magnitude, but it will certainly contribute to the phase. And this is just the overall gain term. And when we plot the magnitude frequency response, we will either plot, you can look at this as either being the magnitude transfer function or the magnitude squared transfer function. But typically when you are looking at frequency response, how do you plot them? You plot versus frequency, do you plot the magnitude or magnitude squared, or do you plot something else? You plot the log magnitude, and log magnitude typically the scale is what is called as the dB scale. So, why is it that you are going to plot the frequency response in log magnitude? Why don't you see this plotted on the linear scale? Okay, so typically you're told that if you have a large range to cover, to see that you will use the log scale. But for example, if this were a filter and if this were a passive filter, then the maximum magnitude gain will be, for a passive filter the magnitude gain maximum will be 1 and the minimum gain will be 0, and 0 to 1 is not a large range, and yet you will find frequency response being plotted on a log scale. No, I think when you are saying it approximate a straight line, you are thinking of Bode plot, and that is log. Here I am talking about the x axis frequency being still linear, but the y axis being log magnitude, and typically it will be 20 log 10 or 10 log 10 magnitude squared. But given that you have 0 to 1 not being a large range, why is it that you still want to plot this on a log scale? So this is typically plotted on a log scale, and you either plot 20 log 10 each of e to the j omega or 10 log 10 magnitude each of e to the j omega whole squared, same thing. Yes, somebody was saying something. Okay, so in the discrete time case, your frequency response goes from minus pi to pi, and if the frequency response, if the impulse response is real valued, you need to restrict yourself only to the range 0 to pi. That also is a finite interval, so that is not a large range. Okay, so you are now looking at a later stage, but if I did not want to do any of that, if I just wanted to plot the spectrum, why would I plot it on a log scale rather than the usual linear scale? So, all of this is coming later. So, if we want to look at this in terms of its contributions to each pole or 0, things like that. The reason why you are going to plot this on a log scale is, if you are going to look at say a low pass filter, and if you are looking at the stop band, and if filter A has attenuation of say 30 dB and filter B has attenuation of say 60 dB. On a linear scale, if you plot these two frequency responses, assume that both these filters have roughly the same passband characteristics, and the transition band, let us say they are similar, but in the stop band is where the main difference is. So, one is say 30 dB rejection, the other is 60 dB, and if you plot this on a linear scale, in the pass band the gain will roughly be 1, and in the stop band you will not be able to see the difference between these two responses if you plot it on a linear scale. If you plot this on a linear scale, if the pass band gain is 1 and the stop band will look roughly 0, but you will not be able to see the difference between these two filters. These are 3 orders of magnitude difference, and you will not be able to see this 10 to the minus 3 versus 10 to the minus 6. You will not be able to see the difference if you plot this on a linear scale. Difference in the stop band of 2 filters that have rejections of 30 and 60, no way will you be able to see this on a linear scale. To see the difference, you need to see this plotted on a log scale for you to make out the difference. And just to give you a feel for what typical rejection is needed, for a filter that is practical, if you want to implement this filter and you want to get rejections that are meaningful, do you have a sense of how much of rejection you should have in the stop band for it to be considered adequate or at least minimum acceptable? Say if I have a low pass filter, pass band gain is 1, which translates to 0 dB. Stop band gain, what kind of attenuation do you think might be needed in terms of dB for it to be acceptable? 60? No. That's a reasonable guess. No, 100 is really large. So, you need at least 40 dB. Any filter that does not even give you 40 dB of rejection in most cases is not adequate. So, you need at least 40 dB rejection in the stop band for you to get adequate performance. So, now let us go back to this and focus on terms like this. So, this magnitude of B naught, once you consider the log plot, all this is going to do is it is going to curve up or down, because this is going to jump out as an added term, and any change in magnitude of B naught will shift the curve up or down. So, we will focus on this, and we have already seen what this can be interpreted as geometrically. So, magnitude of e to the j omega minus zk, geometrically when you look at the magnitude of 2 numbers, complex numbers a and b, magnitude of a minus b is the distance between the 2 points, alright. So, this is, in this case it is now the distance between a point on the unit circle, because e to the j omega is magnitude is 1, and as you vary omega you are moving along the unit circle. Therefore, one of the points is on the unit circle, the other point is zk, which is the 0. So, distance between point on the unit circle and zk, zk happens to be the 0 here. Similarly, e to the j omega minus pk is similar, except here it is now pk. Let us explore this more. So, I have here zk, and then I may have another pole here, and there could also be a trivial pole or a trivial 0. Here I have shown, so Zk should be marked with a filled circle because that is a 0. A cross is the symbol used for the pole, and this is, right now I have shown a trivial pole, this could as well have been a trivial 0. Now here is a point on the unit circle. So this is the point on the unit circle. Therefore, what is happening here is e to the j omega minus zk, its magnitude is nothing but this line segment. Similarly, e to the j omega minus pk is this. Therefore, this is magnitude of e to the j omega minus zk. This is the magnitude of e to the j omega minus pk, and this is nothing but magnitude of e to the minus j omega minus 0. And hence, as omega varies, the frequency response will vary. So, you will start off with omega equal to 0, which means you are on this point on the unit circle, and then you are going to move along the unit circle. You will hit pi, and from pi again you will hit 2 pi. If this were the pole 0 plot of a system with real valued impulse response, the poles and zeros will occur in complex conjugate pairs, and the magnitude response will be even, and hence you can limit yourself to looking at the magnitude response from 0 to pi. So, this is one part. The other part is the geometric interpretation of this frequency response. Therefore, you see that this frequency response can be interpreted as wherever you are on the unit circle, you find the distance from that point on the unit circle to each and every 0, and then you take the product of all such distances. Similarly, for the same point on the unit circle, find the distances to each and every pole, and you take the product of all such distances, and the ratio of these two numbers is the magnitude frequency response at that particular frequency. And this point on the unit circle will vary from 0 to 2 pi. Once you have this geometric interpretation in place, for example, when you are here on the unit circle, you are closest to this 0, which means this distance will be very small. Therefore, the numerator, which is the product of all such distances, the overall product will get pulled down because it is going to get multiplied by this distance, which is very small, and hence the overall numerator will come down in value, and therefore you can expect that the frequency response will exhibit a dip when you are near a 0. Similarly, suppose you are near a pole, which means say you are here on the unit circle, then this particular distance will be very small. So, what was happening in the numerator is now going to happen to the denominator, and hence the product of all the distances will get pulled down because it is getting multiplied by this small factor, and hence the denominator will get small and the overall transfer function will have a large value. Therefore, this interpretation gives you a feel that zeros produce dips in the frequency response, whereas poles provide peaks in the frequency response. Therefore, zeros provide attenuation, poles provide gain. So, this is an intuition that we can develop from the geometric interpretation of this algebraic formula. Carrying this further, suppose this 0 were on the unit circle, then you have this kind of situation. Algebraically, you have e to the j omega, you have here this omega denotes a general point on the unit circle, and since the 0 is on the unit circle, it can be represented as e to the j omega naught. And now as omega varies, when omega equals omega naught, this equals 0 when omega equals omega naught. Geometrically also this can be inferred. So when a 0 is on the unit circle, as you approach the 0, then you will reach a point where you are sitting on top of the 0, because you are on the unit circle, the 0 is on the unit circle, therefore that particular distance is 0 at that particular frequency, and hence the whole product goes to 0, and hence the frequency response goes to 0 at omega L to omega naught. Note that because we are looking at causal and stable systems, a pole cannot be on the unit circle. If the pole is on the unit circle, the region of convergence does not include the unit circle, and hence you cannot quite evaluate the frequency response. Therefore, while the 0 can be on the unit circle and provide you 0 gain, you cannot have a pole on the unit circle to provide infinite gain. But pole can be as close to the unit circle as possible, and it can provide very large gain. So these are the general geometric intuition you can draw from this algebraic expression. And the point about poles or zeros at the origin is, wherever you are on the unit circle, you are at a constant distance of 1, and hence they do not contribute to the magnitude response. Actually, what we have seen is absolutely no different from what was happening in the continuous time case. In the continuous time case, you had h of s, and this was of the form b of s over a of s, and your frequency response was h of j omega, and what you did was you evaluated the Laplace transform by replacing s by j omega. So this is nothing but b of j omega over a of j omega, and this in turn can be written as some general gain pi product of k going from 1 to cap m s minus zk by k going from 1 to cap n s minus pk. And you can think of your magnitude response exactly similar to what was done in the discrete time case. So this is now k going from 1 to cap m, you are going to replace s by j omega, therefore this is j omega minus zk by k going from 1 to cap n, magnitude of j omega minus pk. And this has exactly similar geometric interpretation as what we had just now discussed, only that rather than moving along the unit circle, you are moving along the j omega axis. Therefore, if you have a pole here and say a 0 here and a 0 here and a 0 here, if this were the frequency response, you are somewhere along the j omega axis, and the interpretation of the magnitude response is wherever you are on the j omega axis, find out the distances to all the zeros, take the product, you will get one number. Similarly, for the same point, find the distances to all the poles, take the product, you will get one number. The ratio of these two gives the magnitude frequency response, except for this gain factor. If you ignore this gain factor, the shape of the frequency response is governed by the behavior in relationship to the poles and zeros. Exactly similar to what was happening in the earlier case, if there was a 0 on the units on the j omega axis, when you are going along the j omega axis and you land on top of this 0, the frequency response will go to 0. If the 0 were not on the j omega axis but close to it, when you go past that 0, the frequency response will take a dip. Similarly, if the pole were close to the j omega axis, when you go past that pole on the j omega axis, you will get a gain, you will get a peak. Therefore, poles and zeros shape the frequency response, be it in the continuous time case Laplace h of s, or be it in the discrete time case h of z. So, this is the general intuition. Is there a counterpart to the trivial pole in the continuous time case? Finite S plane. That is a good guess, by the way. The answer is there is no counterpart to the trivial pole case. There it was a trivial pole or a trivial 0 which was at a constant distance when you moved along the unit circle. The origin always was at a constant distance. Is there a point here which is always at a constant distance as you move along the j omega axis? No. Therefore, there is no counterpart to the trivial pole or trivial 0 case that was there in the discrete time system. Such a concept does not exist in the continuous time case. Now, let us get further feel for this. Once you have this geometric interpretation intuition with you, you can kind of guess the shape of the frequency response, rough plot. Suppose I had a pole here, here and here, and suppose I had zeros like this. So, this is the pole 0 plot of the system. And now, what I want to do is I want to get a feel for the frequency response. So, what I am going to do is I am going to start off at this point at omega equal to 0. I will have a certain frequency response. Then what is happening is I am going to go along the unit circle like this. When I am here and I move away from omega equal to 0, what I am doing is I am moving away from this pole. If I move away from the pole, the gain should, will it increase or decrease? It will decrease. Therefore, the gain will start to decrease. I keep going along. When I keep going along, I encounter this pole, which means when I approach this pole, the gain should again start to increase. Therefore, the gain which was at this point started to decrease, and then again it starts to increase when I am roughly in this neighborhood. And then what I do is I keep going along the unit circle, which means I am going away from this pole. When I am going away from this pole, the gain will start to become smaller because I am going away from this pole. Therefore, what is going to happen is the gain starts to fall, and then when I keep going along, I am now going to approach this 0. This 0 happens to be on the unit circle. Therefore, what is going to happen here is response keeps falling down, and when I am exactly on top of this 0, I hit a 0 in the frequency response. Then I go past this 0. When I go past this 0, the gain will increase, and I keep going, and when I hit omega equal to pi, the gain will again has to go to 0. Therefore, the response will be like this. And you can complete the frequency response. So, this is pi. So, you can complete the frequency response for the minus pi to pi part also. Let me so this is minus pi to pi. One thing that I have assumed here is each pole is close enough such that when you are near that pole, it causes an individual bump in the frequency response. If you did not have this information, you cannot draw this plot. The other thing that I have implicitly assumed in is all the heights are exactly the same. Since this is drawn by hand, it is not precisely the same, but the intent is all these peaks are exactly the same point. Even the dips, they have exactly the same dip value. So, this is what is called an equirippled response, and there are filters that have this kind of frequency response that is equirippled, that is these ripples have the same height. Unless I mention that to you, you cannot draw this kind of plot. This is what is called an elliptic filter, all right. There is another kind of filter which is called as the Butterworth. And let me draw the pole 0 plot of a third order Butterworth filter. And the point to note here is these poles, if you look at this plot compared to this, these are clearly further inside. And it so happens that if you plot the frequency response of this filter, the response will be something like this. The placing of the poles is such that when you start from here, the point at which you have the maximum gain, when you go along the unit circle, you are going to move away from this, but this pole is further inside such that even when you approach it, it is not close enough to cause an individual bump in the frequency response. So, the response monotonically decreases and falls down to pi. Therefore, this intuitive sketch based on this geometric interpretation, this rough sketch, implicitly I have assumed that the poles are close enough to cause an individual bump. And to know whether the pole 0 plot corresponds to something like this, that is the frequency response corresponding to this is this or is it this, you will not know unless you feed these numbers into say MATLAB and get the frequency response, alright. But if I tell you that this is the pole 0 plot, and if I also tell you each pole is close enough to cause an individual bump, and further if I tell you that the response is equiripple, then you should be able to come up with a plot like this. And this is a low pass filter, right. This is a low pass filter because it passes frequencies up to a certain point and then beyond a certain point it causes attenuation, alright. And just to quickly continue on that low pass filter example, suppose I had a pole 0 plot something like this. Suppose I had something like this. And then I had zeros wherever. then if I also tell you that this is, the poles are close enough to cause an individual bump, and if I also tell you that the response is equiripple, then you can easily come up with a response something like this. So, clearly when you are at 0, the response is 0, and then when you move along, the response begins to rise, and then when you hit this 0, the response will be precisely 0, and then when you go past this 0, when you are in this region where the poles are, the response will begin to rise, and then when you are near this pole, you will have a bump, and then when you go past this pole, the response will dip, and then we are going to be close to this. So, this pole will cause this bump. Similarly, the third pole will cause this bump, and then when you go past this pole here, then the response will start to come down, and when you hit this 0, so this 0 on the unit circle corresponds to this, and then the next 0 corresponds to this, and this is a band pass filter. So, from the pole 0 plot, given information such as each pole is close enough to cause a bump and the response is equiripple, given this pole 0 plot, you can easily come up with this. And there are 6 poles and there are 6 bumps, 3 from 0 to pi, and similarly so you have 1, 2, 3, 4, 5, 6, 6 poles, 6 bumps. And there are 6 zeros, right? 1, 2, 3, 4, 5, 6. You don't want to count this twice because this point is the same as this. So, this kind of gives you a very quick intuitive feel for the frequency response based on the pole 0 positions.